colloids or colloidal dispersions are kind of like solutions, but the particles are larger. So it's a mixture where you have what is like the solute, a dispersed substance that's finally divided into a dispersing medium. The colloidal particles are small enough that they stay suspended, but they're larger than typical solute molecules. So in a solution, the solute molecules and the solvent molecules are in the same ballpark of size. Here, the particles are larger. They are large enough to deflect light. And so a colloid will have a cloudy appearance. Those particles are typically a nanometer to 1,000 nanometers in diameter, whereas molecules are measured in picometers. So the particles are much bigger. If you look at a colloid under a microscope, the particles are large enough that you can see them. And they have a distinctive jittery motion that's called Brownian motion. And we've got a video here. Okay, fine. We'll do it that way.
My job is to make college easier because students have a lot to learn.
So those are the particles. And see how they're jiggling? Why are they doing that? Short, huh? Come on, let's have a little more of that. So why are they wiggling like that? Are they alive? No. What's making them jiggle around? They're being hit by something too small to see, the water molecules. So if you think of, sometimes they do this at graduation, people throw out like beach balls into a crowd, right? And everybody hits the beach ball. The beach ball just kind of jumps around. And if you're only looking at the beach ball, it's just kind of moving crazy, right? These are like the beach balls in a crowd. We can't see what's hitting them. The water molecules are hitting them. And this was a big deal. So soap forms colloids or colloidal suspensions. The soap molecules form micelles. So this is an illustration of a typical soap molecule. It's got this long hydrocarbon chain, which is nonpolar, and then over here on the end, it has an ionic head. So this end actually has a negative charge. As a solid, this would have a sodium ion with it, but when you put it into solution, the sodium ion and this part separate. So these long tails don't interact with the water very well because water's polar. This is nonpolar. They don't speak the same language. So what happens is those tails that are all nonpolar will congregate towards each other. And those polar heads that are polar and can interact with the water will be on the outside. And it's sort of a circling the wagons, put all of the polar heads on the outside and all of the nonpolar tails on the inside. So the way the soap works to get rid of dirt, grease, oil, those things are nonpolar. They don't wash away in the water, but they can dissolve on the inside of this micelle and sort of then it can sneak out because it's disguised as something polar. These individual particles stay separated because of electrostatic repulsions between the micelles, instead of just all sticking together and forming a different layer. So soap forms micelles. Other macromolecules, large molecules like proteins, will also form colloids. Here's some examples of colloidal dispersions. Fog. Can't see through fog very well, right? Because there's droplets of water in the air. Not individual water molecules like in humid air, but literally water droplets. Smoke is a colloidal dispersion of solid particles in a gas. Whipped cream, yum. Air bubbles in a liquid. Something like milk. Milk is an emulsion. It's got milk fat globules in the water, which is why you can't see through milk. But if you compare whole milk and skim milk has that kind of, it looks like it's almost trying to be transparent, right? Kind of looks watery, right? Because there's less fat. And the fat is what's making it white. And opal, a gemstone, is actually a dispersion of water in silica glass. The Tyndall effect is how colloidal dispersions scatter light. So what we've got here is a strong flashlight going through 2 containers of liquid. In this one, we can see where the light is going through, and in this one, we cannot. This is a solution. The particles here are roughly the same size as the solvent particles, and so no light is being scattered. Here, the particles are too small for us to really see. We don't really notice that it's cloudy necessarily, but when we shine light on it, we see that it is indeed a colloid dispersion because these are deflecting light. And the same thing is happening when you see light streaming in through the window and these sunbeams, right? It's because your air is really dusty, right? If your air was super clean, you wouldn't see the sunshine. All those little pieces of dust or smoke are deflecting the light. Any questions? And that is the end.